Safeguarding personal information from corruption, compromise, or loss has become increasingly crucial. One of the most important developments in public key cryptography, the Diffie-Hellman Key Exchange, was the first widely used method of exchanging keys over an insecure channel. To start off, let's look at a simple encryption methodology that employs a weak shift cipher. Here, A becomes B becomes C becomes D, and so on and so forth. But what happens if we aren't able to coordinate a system, the recipient, and the message beforehand? In this example, X and Y are two individuals who'd like to share information across an insecure channel. They begin by deciding on a common publicly known color yellow, and both X and Y choose their own private colors. X chooses red while Y chooses blue. They then mix the public color yellow with their own private color, with X and Y producing orange and green respectively. Once they've made their color combinations, both X and Y share their mixed colors across the channel, and Z is privy to this exchange. But the ingenuity of Diffie-Hellman lies in Z's inability to decode the messages shared by X to Y. While X is able to add its private color red to Y's combination color of green to produce brown, and likewise Y is able to add its private color blue to X's combination color of orange to produce brown, Z is unable to end at the color brown just given X and Y's orange and green colors. Now let's look at a numerical conceptualization of the same idea using a prime modulus and primitive root. To begin, let's understand a really simple calculation. 32 mod 12. Imagine a string with length 32 wrapped around a clock until the end of the string lands on a number. In this case, it lands on 8. Hence, 32 mod 12 is congruent with 8. Note that in Diffie-Hellman, this modulus should be prime and the primitive root should share no common factors with the modulus. If we look at the different powers of 3 mod 23, we realize that 3 to the power of any number mod 23 has an equal chance of being congruent to any number within the range of 0 to 22, i.e. 23 possibilities. But if we were made aware of the prime modulus and the primitive root, could we also backtrack to find the exponent? For example, 3 to the power of some x mod 17 yields 10. But then how do we know what the exponent is? This is the discrete logarithm problem, which in this case might actually be possible to solve, but consider a prime modulus with hundreds of digits. There's no simple way to compute the exponent then, and theoretically this should require sifting through as many numbers as possible leading up to the modulus. Now let's return to our example from before, but this time with the numerical approach. X and Y are still trying to communicate over an insecure channel, and this time the public information is no longer colors, but that 3 is a primitive root and that 23 is a prime modulus. X chooses the secret number 14, and Y chooses the number 21. X takes 3 to the power of 14 mod 23 to be 4, and Y takes 3 to the power of 21 mod 23 to be 8. Then, X takes Y's public calculation of 8 to the power of its private number 14 mod 23, which yields 11. Similarly, Y takes X's public calculation of 4 to the power of its private number 21 mod 23, which also yields 11. Z, who's privy to the numbers of 4 and 8, finds it incredibly difficult to end up at the final result of 11, hence allowing X and Y to comfortably share information without the monitoring of a third party.